Hello everyone. Now we have to discuss very most important concept in electrical engineering, that is three phase circuits. This concept is very much important in electrical engineering, and in addition with that we are going to discuss why we need three phase circuits over single phase circuits, why three phase circuits are more important than single phase circuits. So we have to discuss all the points here. Before that, first I would like to introduce the single line diagram of power system. Then this is what single line diagram of power system. So what is this means, which describes what? Generation, transmission, distribution and utilization, right? Means which distributes what? This is the part, generation, right? So from here to here we have what? Transmission. Then from here to here we have distribution. Later we have what? Utilization. So the single line diagram of power system, which explains the concept of power system, means we have generation, transmission, distribution and utilization. Means, for example, if you consider a power plant, from that power plant we will have, for example, 11 kV of voltage. 11 kV of voltage. That 11 kV of voltage can be stepped up to some voltage. That stepping up voltage can be transmitted through these transmission lines. Okay, then that transmitted voltage can be distributed towards what? Consumer needs. That's it. This is the single line diagram of power system. Means how much voltage we can generate it, how much voltage we can transmit it, how much voltage we can distribute it, and finally how much voltage that we can utilize in our homes. That is the basic mechanism, right? See, to get clear idea, see, this is the power plant. From this power plant we can generate 11 kV of voltage. See, we have, for example, KTPS. Okay, in that power plant we have, for example, 11 kV of voltage, three phase. Okay, three phase voltage we have generated, three phase 11 kV of voltage. That much of voltage can be stepped up by using what? Step up transformer. That is 11 kV of voltage can be stepped up to what? 22 kV. Later it can be stepped up to 33 kV or 66 kV or 132 kV, finally for example 220 kV. Let us say 220 kV. Okay, see, here we have what? 11 kV is generator power. So 220 kV is what? Due to step up transformer we are having this 220 kV of voltage, right, by using step up transformer. See, this is what? Primary transmission system. At primary transmission system we are stepping up the generated voltage, that is 11 kV to 220 kV. That's it. So from here to here we are having what? 220 kV of voltage can be transmitted to this substation. This is what? Secondary transmission substation. At this substation we are stepping down the 220 kV to, for example, 66 kV. Okay, for example 66 kV. Then from this substation to primary distribution we are having what? 66 kV. So this transmission line, so from here to here this transmission line is required to transmit 220 kV of power, but at this substation that 220 kV of power can be stepped down to what? 66 kV of power. So here I am talking the voltage in terms of power. At this stage, that 66 kV of voltage can be transmitted from here to here. So this is what primary distribution center means, primary distribution substation. At this primary distribution substation, we are having what? Step down transformer. We are having step down transformer. At this stage, we are having 66 kV to 11 kV. So generator power is 11 kV. We are stepping up the voltage to 220 kV. Later it can be stepped down to 66 kV. Now it is stepped down to 11 kV. So from this 11 kV to from this 11 kV, 66 to 11 kV, right? So this much of voltage can be distributed towards what? High tension consumers, means what? Industrial applications. Industrial applications. Or we can step down that 11 kV to what? 415 volts. This 415 is what? Single phase AC. That is line to line voltage. So to get phase voltage, PL by root 3, we are having 230 volts of AC voltage. 230. This is the basic mechanism. See, the generator power is what? The generator power is 11 kV, but we need only 230 volts single phase AC in our homes. So this is the basic mechanism to get 230 volts of AC power, that to single phase from 11 kV of 3 phase from power plant. This is the basic mechanism to get 230 volts or 440 volts line to line voltage or 230 volts phase voltage. 230 volts phase voltage in our homes. See, 11 kV is generated, 220 kV is transmitted. Again, it can be stepped down to 66 kV. Now, 66 kV is transmitted at primary distribution center. That 66 kV can be stepped down to 11 kV. So, from here to here, we have what? 11 kV. It can be stepped down to what? 440 volts line to line voltage. That is 230 volts phase voltage. That's it. This is our, for example, home. We will get that voltage. This is the basic mechanism to get that 3-phase power from power plant to consumer needs. How we can get that power to consumer loads. Okay. So, for example, now we have to discuss why these 3-phase circuits are more important than single-phase circuits. For example, before that, I would like to explain how we can get the EMF. See, for that, here I am considering a single conductor. This is what? Means what? Winding. Conductor means what? We are providing winding in armature slots. For example, this is A, this is A dash. That is, this is one side of conductor, this is another side of conductor. Okay. And we have a permanent magnet. This is permanent magnet. So this is generator, means what? Which can converts mechanical energy to electrical energy, right? Means we are providing some external force to driven this permanent magnet. Then only we can able to get the EMF. That is, when we have some external mechanism. For example, we have a prime mover. By using this prime mover, we can able to driven this permanent magnet. So this permanent magnet is nothing but what? Rotating one. That is, field is rotating. Rotating field. Okay. This conductor is there, no? That is stationary conductor. Stationary conductor. We have stationary conductor and we have stationary conductor, rotating field. So obviously, if we have stationary conductor and rotating field, what we have? Obviously, voltage is induced. That's it. Means by different variations of this permanent magnet, due to prime mover force, this will rotate from 0 to 360 degrees. Okay, for example, these are the flux lines. These are the flux lines. So when we are going to get the maximum flux, when this orientation of this permanent magnet is always perpendicular to this flux lines, then only we will get the maximum flux cutting. When we are going to get the maximum flux cutting, obviously we are going to get the maximum voltage. This is the point at which we are going to get maximum voltage, right? From here to here we are having maximum voltage. This is the place there is no EMF, E is equals to 0. At this place we are going to get maximum EMF. At this place we are going to get 0 EMF. From here to here we are going to get minus Emax, negative value of maximum EMF. At this place we will get 0 EMF. Means what? This is 90 degrees. This is 90, 180, 270. 0 means what? This is the orientation of the permanent magnet, right? 90 means what? This is the actual representation of 90 degrees. See, between this flux lines and this orientation of the conductor, which are displaced by 90 degrees, right? 90 degrees. Obviously, we will have maximum EMF. When this orientation is like this again, we will have 0 EMF. Again, like this is 270 degrees, right? This is 90 degrees. This is 180 degrees. Again, this is 360 degrees. Means what? 0 degrees. So, from 0 to 360 degrees, we are having different voltage. At 90, we are having maximum voltage. At 180, we are having 0 voltage. Like that, at 270, we are having maximum voltage in reverse direction. Finally, at 360 degrees, we are having 0 EMF. That's it. This is the basic mechanism to get EMF by using single phase generator. Single phase generator. We will discuss in detail how we can get this EMF, how many types of EMFs are there in electrical machines when we are going to discuss the concept of electrical machines. Okay, so by using single phase generator, how we can get the EMF? Means generator means what? Which can give electrical energy from mechanical energy. So in order to get that electrical energy, we have to provide some external mechanism. That mechanism is nothing but prime mover. So the prime mover is required to driven that permanent magnet in single phase generator, then only we can able to get the EMF. So the same mechanism can be applicable to three phase circuits. So here we are having what? 3 conductors. This is one set of conductor A dash, like that. This is another set of conductor B dash. This is another set of conductor C dash, right? Means, for example, this is A dash. So after 120 degrees, B dash. Again after 120 degrees, C dash. That is the point, right? So see, here we have 360 degrees. 360 degrees by how many phases? 3 phases. So each phase consists of 120 degrees, right? Each phase consists of 120 degrees. So we are placing the conductors at a distance of 120 degrees between each set. Again we have a permanent magnet. Means when we provide some external mechanism in terms of prime mover, obviously this permanent magnet is driven. So when we are having the rotating field, obviously the conductors are stationary, we are having rotating field, obviously there is a EMF. But we are having what? 3 conductors which are displaced by 120 degrees apart. Obviously we are going to get 3 phase voltages. 3 phase voltage. For example, this is 3 phase alternator. 3 phase alternator. In every power plant we are having this 3 phase alternator. Means what? Synchronous generator, right? For example, From this we got 11 kV of voltage. If we consider KTPS Palvancha, there we have 11 kV of voltage by using what? 3-phase alternator. In every power plant, this is the source to provide 11 kV of voltage. This is the EMF from this 3-phase alternator. Okay, see, this is the representation of alternator. Means what? G. In every system we can represent like this. G means what? Generator. That too, that is 3-phase alternator. That is the meaning. Okay, so this much of 11 kV voltage can be transmitted, distributed, and finally we can utilize that 11 kV of voltage. Means how we can get this 3-phase voltage? Simple, by placing 3 conductors which are displaced by 120 degrees apart, and whenever these conductors are stationary and we have rotating field, obviously there is a voltage. That voltage is nothing but 3-phase voltage. We have completed single phase voltage, 3-phase voltage. This is the basic mechanism to get 3-phase 11 kV of voltage. For example, you consider 11 kV, whatever it may be, this is the voltage from this example. Okay. Now here I am providing, before that, see, from here to here, how many degrees? 120 degrees. Again from here to here we have 120 degrees. From here to here we have what? 120 degrees. See, when this, for example, the red color represents what? R, this is Y, this is B. Okay, red, yellow, blue. Sorry, this is blue. So when this R phase is at 120 degrees, we are having Y phase. When this Y phase is at 120 degrees, we are having B phase, right? That is, what is that meaning? See, so when R is at 0, we don't have any voltage. Of course we are having voltage, but it is having negative voltage, it is having positive voltage. When it is at 120 degrees, we are having Y phase. When Y phase is at 240 degrees, that is 120 degrees, we are having B phase. See, let us say VR, which is equals to V at an angle 0. Let us consider this as a reference. Therefore Vy is what? V at an angle minus 120 degrees, right? Like that. Vb is what? P at an angle minus 240 degrees. Like this we can represent in 3-phase circuits. Why it is 120 minus 120? Why it is? See, if we consider this voltage across R phase is what? Reference. Obviously, after 120 degrees of R phase, we are having Y phase, right? Then after 240 degrees of R phase, we are having B phase. So Vy lags Vr by 120 degrees. Like that, Vb lags Vr by 240 degrees. Means Vb lags Vy by 120 degrees. That is the basic mechanism, right? We can discuss in detail how many connections are possible in 3-phase circuits. We are having in-depth analysis. Don't worry at all. Next we are going to discuss. Now here I am providing some simple trick to draw 3-phase voltage waveform or 3-phase waveform. Further we are having red, blue, and yellow, right? Why? This is Y phase, This is B phase, this is R phase, right? For that, see, first you have to draw with red marker like this. Later you have to change this what to blue like this. Okay, next yellow marker like this. Next red. After red you have blue. Next yellow. Next red. After red you have to change the color to blue, right? After blue, finally, for example, that's it. Okay, therefore after this, yes, you have to connect this point. That's it. See, we are having like this, we have to get. Next yellow. Next see, we are having beautiful waveform, right? See, so like this we are having the three phase. This is what R. Yellow color is what? This is Y phase. Coming to this is P phase, right? See, from here to 120 degrees, again from here to here 120 degrees. Overall from here to here we have 240 degrees. That is, this is a simple trick to draw three phase waveform. Just first you have to take three markers. So alternately you have to draw the lines by changing three markers. Finally we have to connect the outer parts of that lines. We will get three phase voltage waveform or current waveform. Finally, simply it is three phase waveform. Clear? Next, why three phase power is more important than single phase power? Before that, first we have to write in three phase system, instantaneous power is constant, whereas in single phase system instantaneous power is oscillates at twice the supply frequency, right? What is this meaning? We all know that for single phase system, what is the power? Instantaneous power half Vm Im cos phi minus cos of 2 omega t, right? Sorry, cos of 2 omega t minus phi. This is we got average power P average, for example considering R load of Vm Im, that's it, right? Which is equals to what? Vm Im by 2, which for example P max by 2. Therefore in single phase P average is what? Half of the maximum power. So this is the instantaneous power from this single phase analysis, right? Half Vm Im cos phi minus cos of 2 omega t minus phi. So this is for example for R load. For R load, this is the average power, this is the instantaneous power. So in three phase system the instantaneous power is constant, whereas in single phase system the instantaneous power is oscillates at twice the supply frequency. So for that here I am considering a three phase waveform. See here, let us assume this is voltage, this is okay, here they provide 90, 180, 270, that's why this is t axis. If we have pi by 2, pi 3 pi by 2, we have omega t, okay. Let us say we all know that, let us say this is R, this is Y, this is B. So if we consider R phase, let us say this is phase voltage at an angle 0 degrees, and Vy is what? V phase at an angle minus 120 degrees, like that Vb is what? V phase at an angle minus 240 degrees. Clear? Okay. To get clear idea, which is equals to what? We can write V phase sine omega t, which is what? V phase sine omega t minus 120 degrees, which is what? V phase sine omega t minus 240 degrees. For example, in this, let us say this is omega t, this is pi by 2, this is pi, this is 3 pi by 2, this is 2 pi, okay, pi by 2, pi, 3 pi by 2, 2 pi. This is the instant at 0 degrees, right? When omega t is equals to 0 degrees. Therefore Vr is what? Vr is what? 0 volts, right? Vy is what? V phase sine minus 120, we are having minus root 3 by 2, right? V phase. What about Vb? V phase sine minus 240, which is nothing but what? Root 3 by 2 V phase, which means what? See, at this position voltage across resistor is nothing, sorry, R phase is nothing but 0, but see, this is what? This blue color waveform indicates what? Phase B. Phase B is what? Root 3 by 2, satisfied? This is what? Root 3 by 2 V phase. Like that, from here to here, we are having what? Minus root 3 by 2 V phase. Clear? Then, what is the phasor diagram for this? Basic phasor diagram. Here I am providing, let us say, this is Vr. So for 120 degrees, this is V by, like this. This is Vb, anti-clockwise phase sequence. So between these two, we are having 120 degrees. Between 120 120, between 2 we are having 120. This is basic phasor diagram of this 3-phase waveforms. But based upon this, what is the phasor? So VR is 0, clear. Next, what about Vy? Vy is nothing but minus root 3 by 2 V phase. This is positive. Minus root 3 by 2 is nothing but what? This is, for example, maximum V phase, okay, which is equals to maximum value. Okay, minus root 3 by 2 means what? 0.866, means we will get 86.6% of this phasor in reverse opposite direction. Let us say this is minus root 3 by 2 V phase. Okay, next VB is what? As it is, same like, but the magnitude is what? Root 3 by 2 V phase. VR is 0. This is what? VB. This is what? Vy, negative Vy, right? So what is the resultant between these two? How we can get the resultant? So by using parallelogram law, we can get the resultant like this. Then what is the value of this resultant? That is, V resultant is what? To get V resultant, which is equals to, we can apply parallelogram law, that is mod Vy square plus mod Vb square plus 2 mod Vy mod Bb cos of, this angle is what? 60 degrees. 60. Then substitute this Vy Vb in this equation. Finally we got V resultant as 3 by 2. 3 by 2, let us say this is maximum voltage. Okay, see, V resultant is maximum, therefore we have what? V resultant, which is equals to 3 by 2 V maximum. From this we can summarize the power. Therefore the resultant power from 3-phase circuit is what? 3 by 2 times of maximum power, which is equals to what? Which is equals to 3 into 1 by 2 single phase, right? Single phase. So which is equals to 3 times of power in single phase. This is very important observation. Which means what? Power rating of 3-phase system is 3 times that of single phase system. This is very, very important. Then question is, then why not take 3 different single phase systems instead of single 3-phase system? That is a question here. By this we can conclude that what? The power of 3-phase system is 3 times of power of single phase system. Then we have to discuss an important question, that is, why not take 3 different single phase systems instead of single 3-phase system? At any case we will get the power of 3-phase system is what? 3 times of single phase systems. Then why we need only single 3-phase system? So for that we have a beautiful analysis. For that, single 3-phase, for example system. Later we will write generator. Single 3-phase system is more economical than 3 single phase system, that is, now we can write 3-phase generator means what? Means one generator with 3 windings, right, which are displaced by 120 degrees. So, if we require 3 single phase systems, for each system we have some conductor. So, individually we can get 3 conductors, but in coming to 3-phase generator, single generator, one generator with 3 windings which are displaced by 120 degrees. So, to get clear cut analysis, means in a 3-phase generator there is only rotor and hence one speed and common frequency for 3 phases, right. Only we have one rotor. If we consider 3-phase alternator, we have one rotor and one stationary part, that is conductor, which the conductors which are displaced by 120 degrees apart, those are stationary, but the field is what? Permanent magnet which is rotating one. The field is rotating one and the outer part is what? Stationary. So, obviously we are going to get the 3-phase power. But if we consider 3 single phase generator, it is difficult to get same frequency at a time. So, for example, generator A, generator B, generator C, we have a single phase generator A, single phase generator B, single phase generator C. So, it is difficult to get synchronism at a time. It is difficult to get same frequency at the same time. That is why we do not need 3 single phase systems at a time. It is very difficult to get synchronism. But if you take, if we consider single 3-phase generator, because this generator itself consists of 3 windings which are displaced by 120 degrees only, means, but if we consider single 3-phase generator, there is only one rotor, hence we can get one speed and same frequency for 3 phases. Means we are having synchronism between 3 phases. This is the basic mechanism. To consider 3-phase system means single 3-phase system over 3 single phase systems, right. Next, conductor and cost saving, that is, you can write one point. For example, if we consider single phase system, we require 2 conductors. For single phase system, we require 2 conductors. They are go conductor and return conductor. Go conductor means what? Phase. Return conductor means what? Neutral. Right? Which is having power, which is having no power. Means what? This is from source to load. This is from load to source. That is, if we consider system like this, this is load plus minus, this is single phase AC, single phase AC supply. Okay, single phase AC supply. Then this is what? Go conductor. This is what? Go conductor. This is what? Return conductor. So for single phase system we need two conductors. If we consider three single phase systems, we need 3 into 2, 6 conductors, right? See, if we consider 3 single phase systems, we need 6 conductors. That is 3 go conductors, 3 return conductors. But when it comes to 3 phase alternator or 3 phase generator, means what? Single 3 phase generator, we are having 3 to 4 conductor. But when it is comes to single 3 phase generator, only 3 to 4 conductors are needed, or we can say 3 to 4 wires. Okay, so 3 to 4 wire means what? 3 conductors means what? 4 conductors. Before that, first I would like to discuss basic connections are in system are star and delta. Okay, so if we consider star, if we consider delta, that is star means what? How many? Let us say this is neutral. So for this, 1 wire, 2, 3. For this neutral we have 1 wire, right? This is R, this is, let us say this is Y, okay, this is B. okay, 3, this is N. Total we have what? 4 wires, right? But coming to delta, they are having what? Pi this is R, this is Y, this is B, right? For delta connection we need only 3 wires because we don't have neutral point, okay, that's why we need only 3 wires. But coming to star connection we need 4 wires. Let me modify this circuit. So like this we can draw. This is Y. So 3 phase 4 wire system, this is 3 phase 3 wire system. So in case of star connection we have 4 wires, and in case of delta connection we have 3 wires. Why we only have 3 wires? Because we don't have any neutral point in delta connection. That's why in delta connection we need only 3 wires, that is R, Y, B. In this we have what? R, Y, B and N, 4 wires. In this we have what? 3 wires. So what is the conclusion point? The copper saving is very more in 3 phase system compared to single phase system. You can write that point. In 3 phase system, conductor saving is more than single phase system. Sorry, here we can write in single 3 phase system conductor saving is more than 3 single phase systems, right? Conductor saving implies what? Cost saving. That's it. Okay. Next, why don't we use polyphase system, that is more than 3 phase system? For example, for polyphase system we have what? How many degrees over full cycle? We have 360 degrees by M, where M is equals to number of phases. The range of M should be more than 3. Okay. For 3 phase system, 360 by 3, which is equals to 120 degrees for each phase. That's it, right? If we increase beyond 3 phase, then cost increase what will happen? If we increase beyond 3 phase, cost should increase in addition with power rating. Of course, we will get more power, but in addition with that power, we are having more cost. That is not at all economical, right? That is, if we increase beyond 3 phase then cost increase in addition with the power rating, which is not at all economical. That's it. That is cost of, for example, if because 3-phase system is more than cost of 2 3-phase systems. We have exception for 2-phase system. The phase angle between 2 phases is 90 degrees only. This is exception from 360 by M. We will discuss in detail in electrical machines for this 2-phase analysis. Okay, that's it. Why we need 3-phase system over single phase system? The conductor saving is more and cost saving is more, and we are going to get more power, because constant of power we are going to get instead of oscillating power, and we are having more efficiency with respect to 3-phase circuits. That's why we need 3-phase circuits over single phase circuits. Okay.